Okay, you should have out your worksheet on solids and solutions, note sheet for page 5, to be able to take notes on this screencast. This page is on colligative properties and problem solving with colligative properties. Colligative properties are properties that depend on the number of particles in solution rather than the particle's chemical properties. So again, we're dealing with solutions, so we're looking at intermolecular forces at work here and not chemical bonding. So a couple things that are important is understanding the type of solution you have. Do you have electrolytes? Okay, compounds that dissociate into ions when dissolved, so your ionic compounds that are soluble. And that resulting solution conducts an electrical current. So you might hear the word in electrolytes, so that's that connection to electricity. So again, ions in solution will conduct electricity. So strong electrolytes are things that have lots of ions in them. So soluble salts are strong acids and bases, since they ionize 100%. They're going to conduct a large current. Weak electrolytes are weak acids and weak bases. And insoluble salts, so you know from KSP that a little bit of the ions may go into solution, but very little, so they conduct very little current, so not very important. You may be familiar with electrolytes from things like Gatorade and Powerade. They have salts in them, and that's why they conduct electricity and why they're labeled as electrolytes. Your nervous system is an electrical system, so that's why you need to replace your electrolytes when you get dehydrated, so that your nerve impulses get through and do very important functions like telling your heart to beat and your diaphragm to make you breathe. So that's why people die from dehydration. Non-electrolytes are compounds that do not dissociate into ions when dissolved, and their resulting solutions do not conduct electricity. So all of your molecular compounds, so anything that doesn't dissociate into ions, they have negligible vapor pressures even at the boiling point. Okay. And then they're volatile non-electrolytes. These are solutions that do not dissociate into ions but have high vapor pressures. Okay. Things that have high vapor pressure have very strong odors, so things like gasoline. So if you remember that lab we did with the 2 temperature probes, all of those alcohols and alkanes all were very volatile substances because they gave off strong odors and have large vapor pressures. In a solution, we have this phenomenon called vapor pressure lowering, and we call that delta P. So remember, delta, anytime you see that, means change. So the change in pressure occurs because the solution is already more disordered than a pure solvent. So in the pure solvent, the forming of gas particles creates more disorder than the liquid particles lying next to one another. So entropy is going to be something we'll talk about a lot in the next thermodynamics unit. It's called the amount of disorder. So a pure substance is very ordered, a mixture is very disordered. Okay? And that entropy is increased by vaporizing. And disorder is favored in the universe. Just look at my desk at any given time. It's harder to keep it neat than it is to keep it organized, so again, disorder is favored. And this is called Raoult's law. So the change in the pressure of the solvent, and again, this is the vapor pressure, so this is the amount of vapor above the solution. You hear vapor pressure very easily when you open a bottle of soda, so the vapor above it starts to build up, so when you release the seal you actually hear that gas escape. And that's equal to the molality, so the mole fraction of the solute, so that's that italicized X, times the vapor pressure of the solvent. And that little degree means basically the pure solvent, so under normal conditions. So we have a sample problem here at 25 degrees. The vapor pressure of pure water is 23.76 millimeters of mercury. Remember, that's also known as torr. And that of the urea solution is 22.98 millimeters of mercury. So we want to know what the molality of the solution is. So this is another way to determine concentration of solution by measuring this phenomenon. Okay. So pretty much these are plug into the equation, so again, much easier than what we did last with equilibrium. Okay, first thing you have to do is find the change in vapor pressure. So when you do this subtraction, you're going to find that this is 0.78 millimeters of mercury is the change in the vapor pressure. So that's what's going to go in for your delta P value. Okay, so we'll have 0.78 millimeters Hg. Units are nice here because mole fraction is a ratio. As long as your pressure units match, it doesn't matter what they are. So that'll give us the mole fraction of the urea. Okay. Again, you don't have to label that, but again, sometimes it's helpful to keep track of where you are. Times the original pressure, which in this case is of the pure water, so times the 23.76 millimeters of mercury. And just solve for the mole fraction. So 0.033 equals your moles of solute over moles of solution. So knowing that we have 0.033 moles of urea, it's basically taking that relationship, 0.003 moles of urea, and saying we have 1 mole of solution. So I'm going to take 1 minus 0.033, and that's going to give me 0.967 moles of water in this case. So because I'm asked to find molality in this problem, I need to know kilograms of water. So I'm going to convert moles of water to kilograms of water. Okay. So the 0.967 moles of water converted to kilograms, because molality is kilograms of solvent. Just use the molar mass of water and convert to kilograms. And again, if you don't want to do this step, you can do grams to kilograms in your head, that's fine. And then you're just ready to plug that into your molality equation. So you're going to have 0.033 moles divided by 0.0174 kilograms, which is going to give you 1.9 moles per kilogram, or italicized little m. So that's an application of Raoult's law. Okay, another colligative property is called boiling point elevation. So you'll see the change in temperature there for delta T, and the B just means for boiling. And the question is, why would a lower vapor pressure over solution lead to a higher boiling point? And this goes back to what is the definition of boiling point. So think about that for a moment. So boiling occurs when, is the thought that you need to have in your head right now, is when vapor pressure equals the atmospheric pressure. So if the vapor pressure is lower, it's going to take longer for that pressure to build up and be able to boil. So again, if the vapor pressure is lower, it will take more energy to increase the pressure to atmospheric pressure, yielding a higher temperature, because remember, temperature is a measure of the kinetic energy, so a higher temperature means higher kinetic energy. Okay. The equation for the change in temperature is delta TB, so again, B for boiling, equals KB, and again, I apologize that this is another K. You'll always have to look at the context of the problem to see which K they mean. So this is a K sub B, and this is not the equilibrium constant for a base. This is the Molar boiling point elevation constant, and this is measured in degrees Celsius per molality. So again, that should be italicized. M is the molality of the solution, and again, because it depends on particles, that's why you're going to see it using molality, because kilograms has a relationship to moles, where liters does not have a connection to moles, so that's why molality is used. So again, all of these properties are based on particles. And the I value is called the Van 't Hoff factor, and it is equivalent to the number of particles in solution. And this is where it's important to know whether you have an ionic substance or a molecular substance. So if you jump down a few lines here, you'll see for a non-electrolyte, I is always 1, or it's equal to the total number of ions for electrolytes. So when we H2SO4, we get 2 H plus ions, plus an SO4 minus 2 ion. Remember, that's a two-step ionization. So that would be 3. For FeCl3, you're going to get an Fe plus 3 ion plus 3 Cl minus ion. So that gives you a total of 4 ions. Okay. The other thing that's important to note, there is a KB specific to each solvent. So the KB for water is different for the KB for any other solvent. So there's a table on page 509 in your book that is useful for determining these values. So again, on the AP exam, these have to be given to you. If they're not given, that'll be the only variable you'll have to find. They'll give you the change in temperature. Okay. All right, so we have a sample problem here. 33.3 grams of an organic compound dissolved in 150 grams of carbon tetrachloride. Carbon tet is the abbreviation for that, is a very common solvent as well. Has a boiling point of 78.5 degrees. So a couple things that you're going to have to know is what is the normal boiling point of carbon tetrachloride. So its BP, and again, this will be found in tables or given to you, it's 76.5 degrees Celsius, and I believe that's on the same table on page 509. And then the KB value is 5.03 degrees Celsius per molality. So again, these will either be given to you or you'll have a table to get them from. Okay. So the reason you need to know the boiling point is because we really do need to know what's the change in the temperature. So you'll see that this boiling point is higher. So if you think about what happens with boiling, you're trying to get those molecules into the gas phase. By having things in there that don't belong, it gets harder. It creates more attractive forces. So again, if you think about water with an ionic compound, you have that ion dipole interaction, so that's what creates that. So you might know people that put salt in water when they're boiling pasta. Part of it's for flavor, but it also does increase the boiling point, so that makes the pasta cook faster because it's cooking at a higher temperature. So your first step here is going to be to find out what is that boiling point elevation, and it's not a huge amount, so these are usually very small numbers, so you'll see that change in temperature is just 2 degrees Celsius. Okay. And then that's going to be equal to our KB value, which is going to be that 5.03. Okay. And then I need to know what the molality is. I'm going to do a bridge problem, and I hope I can squeeze this all in here in this problem. So to figure out what the molality of the solution is. Excuse me, we need to find the molality first. So that's your X. Again, you can use M for this. Again, I'm trying to make that kind of an italicized, but just make sure you don't cancel this because that's units for you. And since it's organic compounds are molecular in nature, so your Van Hoff factor is going to be 1. So I think I'll try to get this on the next page. So I have 0.40, and because this is in units of little m based on degrees Celsius will cancel out of your problem. This really means moles of compound and kilograms of carbon tetrachloride. So that's important that you understand that. Okay. And we know that we have a 150 gram sample of this carbon of the carbon tetrachloride, and we know we have 33.3 grams of the organic compound, so we're certainly going to be able to calculate the total when we get to the next screen. So from our last screen, we were able to figure out that this was 0.40 moles per kilogram from the change in boiling point elevation equation. So we're going to work backwards now. So we know this, and we're trying to find the molar mass of the compound. So molar mass is going to be the moles of compound. Oops, I won't do that the other way around. Sorry, guys. Grams per mole. So we already have the mole part of this, but we have to figure out how many moles of compound we have from the solvent. So I have 150 grams of carbon tetrachloride. And again, that decimal point was to make the 0 here significant, so this is to 3. Now the change in temperature only gives us 2, so that's probably really a moot point, but so we need 1,000 grams to 1 kilogram, and then we're going to use 0.40 moles of compound per kilogram of carbon tetrachloride. So again, that's what we get from the molality. So this is going to give us 0.060 moles of compound, and we know we have 33.3 grams, so I'm going to have 33.3 grams divided by 0.060 moles. And again, I'm going to keep all of this in my calculator, and you can use your inverse function, again, x to the minus 1, or the 1 over x button on your calculator. If you already have this in your calculator, just hit that button and then multiply by 33.3, and you will get a molar mass of 560 grams per mole. So this is another procedure for determining the identity of a substance as well. So colligative properties are valuable for that as well. The final colligative property we're going to see is freezing point depression. So again, you'll see delta T because there's a change in the temperature, but this time there's an F to show that we're modifying the freezing point. So depression just means the freezing point goes down. So boiling points go up, freezing points go down. So when you're trying to freeze something, you're trying to get it to become ordered. Okay, putting something extra in is going to make it disordered. So think about, if you have a whole bunch of squares that you're trying to organize into, a drawer, and you throw in some things that are circular or that are other shapes. They don't fit together as neatly. So that's basically what's happening here in the solid. So freezing requires a solid to become ordered. Adding different size-shaped particles disrupts the ability of the solvent to become ordered and close enough together to become solid, which overall makes a lower temperature. So again, I'll just read through this one more time for you. Freezing requires a solid to become ordered. Adding different size or shaped molecules disrupts the ability of the solvent to become ordered and close enough together to become a solid. Thus, the freezing point goes down. The most important application of this in your daily life is in the winter when we have inclement weather. They put salt on the roads, which keeps the water from freezing at 32 degrees. Now, even when it gets really cold, as you saw with the boiling point, the changes aren't huge, so when it gets really cold, the salt becomes ineffective at freezing or depressing the freezing point enough that it still doesn't freeze. You may notice if you've ever driven in Maryland, their roads tend to be better. Maryland tends to use calcium chloride as the salt that they put on their roads. With a CaCl2, they have 3 ions, so their Van Hoff factor goes up to 3. Where in PA, we're pretty cheap because we have a lot more roads than Maryland. We tend to use sodium chloride, which has a Van Hoff factor of 2, so it's not as effective at reducing the freezing point, but it does work under normal circumstances. Once you start getting below 20 degrees, that's when it becomes more important to have that third ion in solution to depress the freezing point even more. Okay, and the equation for freezing point depression is very similar to the equation for boiling point elevation. Okay, the thing you have to remember is one goes up and one goes down. And again, so if you can remember that analogy with the salt, okay, it makes the freezing point lower. If you can remember that one, just remember they're opposite, and boiling goes up. So we have a Kf value, and again, this is not the formation constant for a complex ion. You have to use the context of the problem. This is the Molar freezing point depression constant, and that is in degrees Celsius per molality. So again, your M is that concentration in molality, and the I is the Van Hoff factor again. So very, very similar. Again, Kf values are specific to each solvent, and they're on that same table in page 509. Okay, so our problem here is what are the new freezing and boiling points of water if 50 grams of ethylene glycol, that's commonly known as antifreeze, with a molar mass of 62 grams per mole are added to 50 grams of water. So this you'll see both values here. So first thing you're going to have to do is figure out what is the molality of the solution. So grams of ethylene glycol have to be converted to moles, and the 50 grams has to be converted to kilograms. So I'm going to start this problem with 50 grams EG and just using that as my abbreviation for ethylene glycol. So when you convert grams to moles, you get 0.81 moles, and then putting that into your molality, 0.81 moles. And I'm going to just do this in my head. Kilograms is 3 decimal points over, so it'll be 0.50 kilograms of water, which is going to give me a molality of 16. Okay, then I'm ready to plug into my equation. Again, I need to go to page 509 to get my K values. So for water, it's Kb. Okay, so from the chart on page 509, Kb is 0.512 degrees Celsius per molality, or per mole. Kf is 1.86 degrees Celsius per molality. So you can see it's easier to depress the freezing point than it is to elevate the boiling point based on the values of those numbers. So these are just going to plug into your equation. So the delta T B is going to be your 0.512 degrees Celsius per molal times 16 molal. And ethylene glycol is also organic, so molecular. So that's a von half factor of 1. Okay, it would be sodium chloride, you have 2 ions, your von half factor would be 2. So this gives you 8.3 degrees Celsius. Okay, and it's boiling point elevation, so normal boiling point of water is 100. So your new boiling point would be 108.3 degrees Celsius. Okay, and then for your change in freezing point, it's going to be 1.86 degrees Celsius per m molal times 16 molal, again times 1. It's going to give you 30 degrees Celsius. So again, this is why ethylene glycol works so well as an antifreeze. So the freezing point is going to go down. So the normal freezing point is 0 minus 30. It's going to give you a new freezing point of minus 30 degrees Celsius. So that's why your antifreeze works to keep the water in your car's cooling system from freezing in cold weather.